All right, why don't we go ahead and get started here? It's a few minutes after 3 o'clock in Seattle. For those of you who are joining elsewhere and don't know me, my name is Rory Barnes, and I'm going to be hosting this seminar today, and it's my pleasure to introduce Zoe Todd from Harvard University, who will be today's speaker. Zoe began her career at Penn State University, where she triple majored in astronomy, chemistry, and physics. She then took that knowledge to Harvard University, where she's currently in the astronomy department, working with Dimitar Sasolov, but also has been collaborating with Jack Shostak and Karen Oberg. She has recently defended her PhD, so congratulations to Zoe on that fantastic accomplishment. And we're really delighted to have her today at the seminar because she is going to be moving to Seattle this summer, we hope, to join Professor Kathleen and his group here in Earth and Space Science and the Astrobiology program. So from that introduction, I'm sure you can guess that Zoe has some broad interests, and she's going to be telling us about her research on the planetary environments and that lead to the origin of life. And of course, this is a great sneak peek for those of us who are here to learn not just about the research that she's been up to, but also to get a glimpse of the experience and expertise that she's going to be bringing to us here in Seattle. So before I turn it over to Zoe, I want to reiterate a couple points I made in the chat room there, namely that I'd like to, if you can, to please not interrupt the presentation today with any audio or video questions, but rather to type them into the chat room. And then at the end of the presentation, I will be happy to convey your question to Zoe. And also for those of you who are on the line, please do mute your microphones and stop your videos during the presentation so that Zoe can have all the bandwidth that she needs to give this presentation. So with that, I think I'm going to stop talking and turn it over to Zoe for today's seminar. Please take it away.
All right, well, thank you so much, Rory, for that very kind introduction, and thank you all for showing up and for the invitation to be here. I really can't tell you how excited I am not only to be sharing my work with you today, but to be coming and joining the UW Astrobiology community in the fall. Really looking forward to that and looking forward to all the knowledge that we can share and all the ideas and collaborations that can go on there. So today I'm going to be talking about what can the planetary environment tell us about origins of life. So as Rory mentioned, I come from a background both in astronomy and chemistry, and I've been trying to merge these fields together to understand and push forward our understanding of the origins of life. So if we think about perhaps one path towards the origins of life, it might go something like you have a very simple environment available abundantly on the surface of a planet, whether it's getting simple feedstock molecules from the atmosphere, from lightning generation, from photochemistry, or from impacts. You have these very simple, 2 or 3, maybe 4 or 5 atom molecules that are robustly available on the surface of a planet. Then if those simple feedstock molecules can come together and react and form the precursors of life, so stepping over here into box number 2, so here I'm thinking more along the lines of biomolecules, such as your sugars, lipids, nucleotides, and amino acids. So that's one step towards getting the origins of life, but even then you're not done yet. So at that point, then you need to have these simple biomolecules come together to form polymers. So you need to get your genetic information, perhaps an RNA world where you have RNA as the genetic replication system there, or you need to get your amino acids polymerizing to form peptides to gain some enzymatic functions, and also transition to a protocellular world or a cellular world with lipids forming membranes or vesicles here. So this is one path outlining a possible origins of life, and I'm going to be discussing a couple of steps in this context, and especially considering how the planetary environment can inform the chemistry for origins of life, and furthermore, what sort of constraints the chemistry for origins of life can show us about the planetary environment. So with that, I'll jump right into the first project that I'm going to talk about, which focuses a little bit on this step here, where you're synthesizing the precursors or the simple biomolecules of life. So, all right, in this project, I'm going to be talking about some photochemistry of pyrimidine ribonucleotides. So we have a nice picture of the sun emitting in the UV range, and then we have a generic pyrimidine molecule right here. So if we think back to the spectrum of the early sun on the surface of the early Earth, The Sun-Earth system at the time of prebiotic chemistry, for some billion years ago, would have been very different from today. So this is coupled from a couple of different facts. So first off, the sun at that time was going to only be about 70% of its current luminosity as the star evolves and comes onto the main sequence. And we also have a larger fraction of the light is going to be output in the UV region from the sun at this earlier time. But perhaps the biggest difference is going to be the composition of the early atmosphere at the time of prebiotic chemistry. So before life, before the great oxygenation event, we would have had very little oxygen and ozone in the atmosphere of the Earth. So this means that these species which are present in our atmosphere today and actually block out a lot of the UV light from hitting the surface of our planet today would not have been there. So you would have UV light down to much shorter wavelengths than we get on our modern atmosphere. So a reasonable thing to ask is, what is the spectrum and what are the expected fluxes of UV light under this system of the sun-Earth during the time of prebiotic chemistry? So a former grad student in Dimitar Sasilov's group, Sukrit Ranjan, did the theoretical calculation and prediction for what sorts of fluxes and wavelengths of UV light you would expect on the early Earth. And he found that you get UV light down to about 200 nanometers, and there's a very sharp cutoff here due to the presence of CO2 in the atmosphere. But you do get UV light all the way from 200 nanometers up through 300, 350, all the way through the visible. However, you'll note that this is a log scale, so you get a lot less photons coming out at these very short wavelengths than you do at the longer wavelengths. But this is a theoretical calculation for how much UV light you get through a sample prebiotic atmosphere on the surface of the early Earth at the time of prebiotic chemistry. So why do we care about UV light so much? Well, there's a lot of energy that is available from UV light, and it's a very robust source on the early Earth. So people have been trying to use UV light as a photochemical process to drive prebiotic reactions for many years now. And oftentimes when you're in the laboratory and you're trying to do these experiments and just get your experiment to work, you want to make it easy on yourself because many things can go wrong all the time, even under the most perfect conditions. So people often use a very cheap, powerful, and easy source of UV light, which is these mercury emission lamps that are shown here in this pretty awesome picture. And if you think about what the spectrum of UV light is coming from these mercury emission lamps, it looks something like this. So here, if you focus on the UV region, you see there's this narrow band emission centered at 254 coming from these mercury emission lamps. Now, if we compare this spectrum of UV light coming from these lamps that we use in the laboratory compared to this spectrum of UV light that you would expect on the surface of the early Earth, you can see that they are very, very different. So here you have broadband irradiation from 200 nanometers upward, and here you just have narrowband emission centered at 254. So a reasonable thing to ask then might be, if you have a prebiotic photochemical reaction that you demonstrate works in the laboratory under these conditions, 254 nanometer light, would it also work under the UV environment present on the early Earth? So that's kind of the motivation for some of my work and some of what I'm going to be discussing today. So what's one example of one of these prebiotic photochemical reactions that uses UV light to do productive chemistry to make the building blocks of life, these biomolecules that we want to be able to eventually synthesize in order to polymerize and get to a protocell? So this is a really neat synthesis published by Pauner et al. 2009 in Nature, and they found a synthesis to get to the pyrimidine ribonucleotides. So these are C and U, two of the letters of RNA that are used in life today. So canonically, the way that people have thought about doing this is you take a ribose and you take the nitrogenous base and you try to just jam them together and form the glycosidic bond, which is located right here. You can see this nice red X. This indicates that historically, this reaction has been very difficult to make function. So when it does occur, it occurs with very low yields and not very good efficiency. And for some bases, it actually doesn't seem to occur much at all. So this has always been a roadblock towards synthesizing the ribonucleotides, where you have the sugar, the base, and the phosphate as well. So one potential way to get around this that Pauner found was you take very simple molecules, so things like glycolaldehyde, glyceraldehyde, cyanamide. You can use this mixed oxygen-nitrogen chemistry to synthesize the nucleotide basically all at the same time and avoid having to form this problematic glycosidic bond that is challenging to form under some cases. So this was a way to get to C, which is shown right here. So this is cytidine, one of the letters of RNA. And then the really neat thing about this paper, or one of the really neat things about this paper, in my opinion, is that once you get to C, Pauner et al. Showed that if you irradiate this nucleotide here with UV light, you can partially convert it into U, uridine, another letter of RNA. So this is a way to basically get 2 nucleotides for the price of 1. So all you need to do is get your synthesis of C, then invoke the use of UV light, which we know would be abundant on the surface of the early Earth, as I showed in the previous plots, and then you get uridine as well. So how might this actually work? So there's a number of steps that would actually go into the conversion of turning C into U. So for those of you who are not chemists, I've tried to indicate which species is which as I'm talking about them. So this C, bracket P, I will sometimes call this cyclic C just to refer to the fact that it has this cyclic 2', 3' phosphate, which is the specific species that Pauner et al. Synthesize here. But I don't draw all of the molecules in this plot here. So this C, if you irradiate it with UV light, you could potentially form a photohydrated intermediate where you put a water bond across the double bond here. So this is the mechanism that is known to undergo for cytidine and for cytosine, but it's not sure. We're not sure if the cyclic phosphate with this 2', 3' linked phosphate here would undergo this mechanism shown in A or this mechanism shown in B. So I'm not going to focus too much on the mechanism here. For the purposes of this paper, we decided not to try to identify the intermediate explicitly, but rather consider what the planetary implications for this reaction are. So getting back to the point here, you have C and you can irradiate it with UV light to form an intermediate, either this one or this one. Now this intermediate, if you have water, can come in and deaminate. So you kick off this ammonia group here and then form basically the uridine adduct of this intermediate, which then if you have heat can recover U. So this is your way to get the 2 canonical nucleotides, C and U. So important things from this plot, or this scheme here, that if you have C or U, if you irradiate them with UV light, you push them inwards towards this intermediate or photodamaged state. And then to get out of this intermediate photodamaged state, you invoke heat to go back to the nucleotides here. All right, sorry for the chemistry. I will try to make this as understandable as possible, but feel free to ask me questions at the end if it's totally unintelligible. So in Pauner et al. 2009, they did this irradiation with UV light to turn C into U, but they used that 254 nanometer mercury lamp irradiation. So again, we want to understand what the context for this reaction is on the surface of the planet in the planetary environment. So we wanted to understand how the reaction depends on the UV environment available on the surface of the early Earth. So to do this, we wanted to test the wavelength dependence of the reaction. And the experimental apparatus that we used for this is shown here, where you have a 75-watt xenon lamp located here. You can pass this through a diffraction grating, which basically is a prism and acts as a monochromator, so that you can select for individual or pretty narrow band wavelengths. So we could irradiate solutions at 215 nanometers or at 225 nanometers, so on and so forth. Pick whatever wavelength you want, and you can do the irradiation there. So that's essentially what we did for this first step here. So back to this mechanism. Right now I'm just talking about taking this C initial material and turning it into this intermediate with the use of UV light. And so what we can do is we can observe this reaction as it undergoes irradiation by UV spectroscopy. So this initial material, this C, has an absorption spectrum that looks like this darkest blue line shown here, where it's at the top of this 270 nanometer feature and at the bottom of this 240 nanometer. So when you irradiate solutions of C, we can see that the absorption feature at 270 nanometers decreases, while the one at 240 nanometers increases. So the 240 nanometer feature is due to this intermediate, where the 270 nanometer decreasing is due to loss of the starting material. So from these spectra, we can determine the concentrations of both species, both the starting material, C, and the intermediate product that we're forming. From this, we can determine the rate constant for the reaction by plotting the logarithm of concentration as a function of time. You can see we get nice, clean, linear lines here. And so this example that I'm showing is for 265 nanometer irradiation. But again, we want to know how this reaction behaves at different wavelengths. So we tested the wavelength dependence of the reaction by irradiating from 215 to 295 nanometers in 10 nanometer intervals in the 10 nanometer band. Then to be able to compare the reaction rate constants at various radiation wavelengths, we also have to normalize for the instant photon flux because the lamp doesn't output the same photons per second at all wavelengths. This is a way to just be able to compare apples to apples when we're looking at rate constants. So when we look at that, this is what we see here, where you have rate constant as a function of a radiation wavelength. And we again did this from 215 nanometers all the way up through 295 nanometers. And when you look at this, you can see that the most efficient wavelength for doing this is 265 nanometers. So I see a chat question from somebody who asks, under what conditions can you release the NH in the structure of this molecule? So basically, if you have C, or even just if it sits in water over enough time, water can come in and kick out that NH, the ammonia group, and cause deamination and conversion into U. This occurs much faster when you have this UV-driven step, and I'll show you some data that indicates that later on. So this happens fairly spontaneously, but there is some sort of activation energy that needs to be overcome, which is driven by the UV light. So thank you so much for the question. Feel free to chat Zoom questions, and I will try to answer them as I go if I can, but no promises. Okay, so the 265 nanometer irradiation was shown to be the fastest rate constant here. And then we can see that the rate constant drops off as you go to higher wavelengths and also shorter wavelengths in this region. So you might say, all right, well, you promised to tell me what this reaction means in the context of the planetary environment and the UV environment present on the early Earth. So I haven't quite done that yet, which is what I'm going to describe now. So we want to ask what happens on the early Earth then. Well, in this green line, I'm showing you that theoretical calculation for the spectral flux from 200 to 300 nanometers from Ranjan and Saslov 2016. So again, this is showing us our broadband irradiation from 200 to 300 nanometers with the variant fluxes. Now we can take that theoretical prediction for how much light is coming through and integrate that up in the same 10 nanometer intervals that we did the experimental irradiations at. Then multiply together the integrated flux in that wavelength range with the experimentally determined reaction rate constant at that wavelength. The product of those two is what we call the relative rate of the reaction, which is what I'm showing in these blue points here. So this relative rate takes into account not only the rate of the reaction as a function of a radiation wavelength, but also the amount of light that you would expect at that wavelength on the early Earth, according to this theoretical prediction. So when we do this, we see that there's a very clear window for the most efficient radiation, which is from about 255 nanometers all the way up through 285 nanometers. So from this, what we take away is that the reaction should be able to work on the UV environment on the surface of the early Earth. So there was nothing specific about that 254 nanometer radiation from mercury lamps that was first done in Powner et al. 2009. That is the only wavelength that works. That's not true. This process should work across a range of wavelengths and most efficiently from this 255 to 285 nanometer region. Okay, so that tells us about the first step here of taking the C and turning it into the intermediate here, which is a UV-driven step. But as you can tell from the numerous other chemical structures shown in this mechanism, that's not the end of the story, because after all, we want to ultimately get U out of this as well, in our way to get 2 nucleotides for the price of 1. So moving on to the next step, or the next thing to consider, is that once you have this intermediate that is formed by UV light, With the presence of heat or just sitting in the dark at a certain temperature, it will revert and turn back into the starting material, at least partially. So we wanted to investigate this step as well to understand what was going on. So the way that we did this is do the irradiation, turn your C into the intermediate as completely as you can, then let your irradiated solution sit in the dark at different temperatures. So here I'm showing you at 35 degrees Celsius, the concentrations of these two species. So you start out with pretty much all of the intermediate after the irradiation, and then as it sits at this temperature over time, the intermediate decreases and you see a build-in of the starting material, the C, returns. Now we can do this reaction at a variety of different temperatures to be able to generate what we would call an Arrhenius plot, where you get the log of the rate constant as a function of inverse temperature. And from the slope of this line, you can determine the activation energy for this reverse reaction of turning the intermediate back into C. And this activation energy we found to be around 85 kilojoules per mole. Okay, so this takes us still in the first block of this mechanism here, where we have C and we're turning it into this intermediate, or we're turning the intermediate back into C, either through the presence of UV light in the first case or the presence of heat in the second case. But still, I haven't said anything about U. So now let's consider what happens to U. So when you have this intermediate, you can have the deamination occur when water can come in and kick out ammonia and form the uridine form of this photohydrate over here. However, to go from this uridine photohydrate back to uridine itself, this requires a significant amount of heat, a lot more heat than to go from this C photohydrate back to C. So that's why we don't see the presence of U in those previous experiments, because you need more heat for longer periods of time. So you could believe me when I say that, or I could also show you the data to prove that. So I will do that here. So here what we did is we did a very similar experiment to the previous one, where you irradiate a solution of C, form the intermediate, and then let this irradiated solution sit at high temperatures for an extended period of time. And we can see that initially what happens is you go back to a UV spectrum that resembles C, the starting material. But then with more time at this high temperature, you see the absorption peak shifts slightly from about 270 nanometers over to 260 nanometers and continues to grow. So this is indicative of the absorption spectrum of U. So we're starting to see the U material come about. From these absorption spectra, we can extract a concentration of these three species, the C, the intermediate, and the U. And you can see that as a function of time, we initially get this return to C, but then over longer periods of time, we do get U coming about. So this is just to prove that we do indeed get U from this conversion of C and driven by UV light. So at this point, you might be wondering, well, is this really useful, or what's the prebiotic plausibility of this? Because it takes you 100 hours to really get a return to U. And this, again, needs to occur in the dark outside of the presence of UV light. Otherwise, you're pushing yourself back to the photohydrated or intermediate state. That's a good point, and I will come to address that a little bit more as I continue to go on. But first of all, we wanted to see how the irradiation characteristics affect how much C and U you get ultimately. So what we can then do is irradiate these solutions for varying amounts of time. So anywhere from 0 minutes, 10 minutes, all the way up through 2 hours, and see how after you let them sit for 100 hours at 60 degrees Celsius, how much C and how much U do you get at the end. So you can see that we get fairly consistent levels of U at the end of this 100 hours of heating after these various irradiation times. So you get less and less C as you go to longer irradiation times. This is perhaps not surprising because this UV light is converting C into U, and then this decrease of C and not corresponding increase of U indicates that there is some irreversible photo damage going on as this process occurs. So it's not 100% efficient and you're not turning all of your C into U, but there's some other stuff going on. So automatically you can see that this will put some sort of limit on the amount of time and the amount of C that you will have around under planetary conditions based on the amount and the time of UV light. So that's for continuous irradiation. But what about for something a little bit more subtle, like irradiation cycles? So what we did here is we took a solution of C, irradiated it, then let it sit at a temperature in the dark for a certain amount of time, then do cycles of this. So irradiate it, let it sit in the dark, irradiate, let it sit in the dark, and see how much material we repopulate with each successive cycle. So you can see that after each irradiation step shown here, you get correspondingly less material corresponding to the intermediate. And then after the thermal steps in the dark, you also get less of the C, the starting material, coming back with each successive cycle. So again, we're getting a loss of material with these irradiation cycles. On average, you only recover 88% of the initial material after each successive cycle. So this can be due to irreversible photo damage, perhaps loss of the nucleobase, but also conversion of this C material into the U photohydrate, that U intermediate, that then ultimately can relax to U if you let it be heated for extensive periods of time. But what you can see here is if you're looking from the perspective of how much C do you have and how long will you have it on the surface of a planet, this sets a limit for how long and what concentrations you can have. So if you have unprotected conditions where your material is subjected to UV light continuously or in cycles, you're going to deplete this material. So we think physically about what these experiments represent. Irradiating in the light, then sitting in the dark, and irradiating in the light, sitting in the dark. This corresponds to a very simple physical process that occurs on planets all the time, and that would be the day-night cycle. So what we can then do is take the experimentally determined parameters for this set of reactions and try to model what a day-night cycle is and how that influences these reactions. So what we did is we took those wavelength-dependent, experimentally determined reaction rates and then integrated that over the entire 200 to 300 nanometer wavelength range that you would expect on the early Earth to get the total rate of degradation you expect under the UV environment on the surface of the early Earth. So that's going to be the UV-driven step of converting C into the intermediate. And then we also have the experimentally determined recovery rates of the intermediate back into C as a function of temperature from that Arrhenius plot that I showed previously. So then what we can do is we can take a sample day-night cycle where we allow the day, the length of the day to be only 16 hours instead of 24. So here I'm showing the concentration of C, the starting material. If you assume you have 1 millimolar initially, you can see how long does this material last under various conditions. So this first step downwards is showing us the first day. So this is 8 hours of light where the irradiation wavelength dependence rate averaged over the entire wavelength range is causing a depletion of your C and turning it into the intermediate. Then we have 3 different temperatures that we're allowing the material to recover at thermally, and this returns varying amounts of the material. And at this highest temperature, where you do get almost complete recovery, we impose this 88% limit of return from each successive cycle that we saw experimentally to show that you're actually depleting this material over time. So you can get an estimate for lifetimes of this starting material, this C, under these conditions. We find that at the coldest temperatures, your starting material might only last for a day or 2, maybe 3. And at your higher temperatures, your material will last above these micromolar concentrations for several hundred hours likely. Okay, I have another chat question. Would these reactions occur outside an early Earth atmosphere, say on a body continuously exposed to solar UV? So I would say anywhere there is UV, there will be these reactions occurring. But the question then that I would ask is there aqueous water around and is that going to change? So if this is not occurring in aqueous solution, I would not be able to say precisely that our reaction rates and our mechanism would occur under that circumstance as well. But if you did have an aqueous condition, but you were on some body with some sort of atmosphere that could allow for water to exist, I think this reaction would also occur there. Not sure if that was sufficient to answer your question, but I appreciate it and let me know if it wasn't, and I can try to revisit. All right, great question, by the way. Okay, so from this model day-night cycle, what we can do then is say, Well, one way to look at it is if you start with this amount, see how long it will last. But an alternative way to look at it is say, if I want to have this amount continuously and it's being degraded at this rate, what is the production rate that I need the chemistry to give me in order to sustain that steady state? So if we want to have 0.1 millimolar of C in a steady state concentration, for these various temperatures, you need these production rates. They're somewhere on the order of 1 to several micromolar per hour, depending on the precise temperature that you invoke. So then this is a way of, we took the chemistry, we tried to understand how it would react under the environment on the planet, and then take the constraints that are implied by that planetary environment, and then we can give these numbers back to the synthetic chemists and say, can you get this C production synthesis to give me rates of micromolar per hour? Or if not, then we need to start thinking about other environmental scenarios here. This is again an interplay of the chemistry informing the environment and the environment informing the chemistry. All right, so takeaways from this. The photochemical conversion of C to U should work under the irradiation environment on the early Earth with a maximum wavelength at 265 nanometers and a usable region from about 255 to 285. However, if you have prolonged irradiation, you're going to lose your C, your starting material. And from this, we can estimate the production rates that would be necessary for steady state concentrations. And if it turns out that the chemistry cannot provide you with the sufficient production rates for the steady state concentrations that you think you need for the chemistry to function, then you have to consider an environmental scenario where perhaps you have shielding from UV irradiation at specific locations or specific times. So there are many thoughts of what this could possibly look like, but there's a lot of work that could potentially go into that. So I'm happy to answer questions about that at the end. I'm not going to discuss it too much more right now. So another important thing to mention here is that there are other ways to convert C into U. This is not the only way. So this will happen spontaneously but slowly in water. Using nitrous acid is a really efficient way to convert C into U. And then another potential quagmire with this is that when you get to this U intermediate, that uridine photohydrate, we saw that we needed like 100 hours at 60 degrees Celsius to recover uridine, and that needs to occur in the dark. Otherwise, you're going to put yourself back into that photodamaged intermediate state. So is that prebiotically possible? That's another question. Perhaps there are ways to get around that, and this is something that I'm trying to work on these days. Or as soon as we're allowed back in the labs, we'll hopefully get some more results on that. But the whole idea here is that hopefully we can use the results of examining this reaction in the context of the planetary environment to get a better idea of the constraints for the chemistry to work, what sort of geochemical and planetary scenario we would need. Okay, so that's kind of the wrap up of the first project that I'm going to talk about. And just if we put this back in the context of this scheme here for a possible path for origins of life, where you go from the environment to simple precursors of life to eventually protocells, we were kind of in this step right here, where you're looking at getting the precursors of life and specifically what the role of that UV light was. But what if we take a step back and we want to consider, well, how did you get those simple molecules in order to be able to make those building blocks of life, to make that C and to make that U? Well, then we need to consider the planetary environment that would be available, hopefully robustly and abundantly on the surface of the planet. So that's what I'm going to be talking about in this next project here. All right, and so for this, I'm going to be talking about cyanide impact chemistry. So for those of you who are astronomers by training, you've probably seen images like this, where this is an image from ALMA, the Atacama Large Millimeter Submillimeter Array, where you get these beautiful images of protoplanetary disks where you can actively see these rings that are thought to be places where planet formation is going on. You can also look at these protoplanetary disks and see molecules. So for example, this is showing you HCN here. We also look out in our own solar system and we see the remnants of planet formation in the form of comets. When you look at comets and you can detect molecules spectroscopically in comets, we see that one of the more abundant molecules is hydrogen cyanide. There are a vast range of different organics and molecules contained in comets that we see today. Then another motivation for this is that we also, if you look in the inner solar system, look at our moon, for example, or Mercury or Mars even, we see impact craters all over the place. We see less of these on the Earth just because the Earth has active plate tectonics that erode and overrun these craters, so we have less history of that. But that doesn't mean that things didn't hit the Earth. If we look around the inner solar system, we see the impact craters are robust and abundant. So it's reasonable to assume that the Earth also was impacted by lots of bodies. So if you had, say, a comet that contained a lot of organic molecules, for example, perhaps this HCN, and it hit the early Earth, could it have delivered any of that material to be used for prebiotic chemistry? So that's kind of the context for this project that I'm going to be talking about next. So how much HCN initially contained in a comet would survive to be delivered. Why do I focus on HCN, you might be asking here. So I'm going to describe a little bit of motivating this. And again, sorry to all the non-chemists in the group. I frequently show this slide here, and some people just look like they want to run away screaming. The nice thing is I won't know if you do that because all of your videos are turned off. So I'm just going to pretend that everybody's good with it. But I'm going to step through this so that hopefully it won't be quite so terrifying. So this is an example of cyanosulfidic photoredox network that has come out of John Sutherland's lab in Cambridge. This was published in Patel et al. 2015. And this is a really neat network because it is a way to get all 4 major biomolecules of light from a very simple unified set of precursors. So I'm going to step through those right now. So you can see these 2 molecules here. We have glycolaldehyde and glyceraldehyde, which are these are then used in a variety of other reactions to make things like your lipid precursors. So we like lipids because lipids will spontaneously self-assemble in an aqueous solution to make membranes, things like vesicles, which can act as protocells and potentially be the precursors for cellular life. They can also give you a lot of advantages for getting chemistry to work and for doing fun things that would be an aid for prebiotic chemistry. So we get sugars, we get lipids. We also get 12 amino acids in this pathway total. So this actually does better than the canonical Miller-Urey experiment of lightning generation in the atmosphere to give amino acids among other organs. And then we also get the pyrimidine ribonucleotides. So this here is that C that I was talking about in the previous project, and here is the conversion into U using UV light. So that's all 4 major biomolecules that life uses from this network. But where do these actually come from? Well, shown here in red is hydrogen cyanide. And pretty much every single carbon and nitrogen that you see in this diagram was originally contained in a hydrogen cyanide molecule. So this is why this network is called cyanosulfidic, the cyano for cyanide. And then the sulfidic comes from the use of either sulfide or sulfite. So in this case, this is sulfide, H2S, and I've circled where sulfur appears in some of these molecules. And this can be used to drive the chemistry as well. And finally, last thing to mention here is the photoredox network. So the photo part means it makes use of light, and specifically UV light in a couple of key circumstances. So this step here was what I talked about in the previous project, so turning C into U using UV light. There are other steps along the way to drive the photochemical reduction of hydrogen cyanide to make these simple sugars and in other parts as well. So this was all motivation for why am I going to be talking about cyanide? Well, we like cyanide for prebiotic chemistry because it's very robust and volatile and can make a lot of these molecules. And it hasn't just been invoked in this network for prebiotic chemistry, but all the way back to Oro's work in 1960 showing that adenine is actually a pentamer of HCN. So HCN is of robust prebiotic importance and relevance. So this is the question we want to address in this project. How much HCN survives a cometary impact to potentially be delivered to the early Earth? Because we see HCN in space, we see it in protoplanetary disks, in comets, and we know that things hit the early Earth. And we like hydrogen cyanide for prebiotic chemistry, so that's what we're trying to find here. All right, so the way we did this is we constructed a chemical kinetic model where we take temperature profiles as a function of radius inside of a simplified spherical comet. We pulled these from literature models that have been run in the past, where you have your innermost shell is going to experience your lowest temperature profile overall. And then you get correspondingly higher temperatures as you go outward in the comet, and things become less shear. So our comet contains initially 4 molecules only. We have water, HCN, CO2, and CO. So the first thing that happens is you can degrade those molecules just based on thermal decomposition into their subsequent reactive radicals. So things like H2O break apart into H and OH. And once you have these reactive radicals, they're going to react with each other and with the other species. So specifically, if we're looking at HCN survival and degradation, so HCN can be degraded by reactions with OH, and these products form, or by reactions with O to form these products here. Then you can have further reactions with nitrile chemistry, where your CN bond in some of these products can either be converted back into HCN or be destroyed completely and converted into other products as well. So that's the nice scheme of showing this chemical kinetic network, but just to show some of the reactions, or all of the reactions. So we start out with those 4 molecules, and you might be thinking to yourself, wow, 4 molecules, this must be a really simple project. Why is this so hard? So basically, when you have these 4 molecules that degrade into these reactive radicals, then you open yourself to a host of new reactions, and many more new reactions. So I think we have a total of 75 or 77 reactions and about 31 species total, if I am remembering correctly, that we take into account. And I would just tell you right away that we are not complete with respect to all of the chemistry that could occur in this chemical kinetic network, but we think we're fairly complete with respect to the cyanide. And we also ran a control model without this additional chemistry, but just looking at the HCN degradation reactions to make sure that we were able to recover results. All right, so I have a chat question that asks, how difficult is it to form HCN from CN? CN has been found in meteorites too, but abundances are low. So I would say forming HCN from CN is going to be the easier part. The important part is really that you have that CN triple bond intact. So that is what is robust and provides the chemical versatility that is necessary for a lot of these prebiotic reactions. So if you have CN in meteorites, I would say that's awesome. That's great. Yes, of course, abundances are going to be low, but still shows us that some survival is intact. So that's great. I actually didn't realize that CN was found in meteorites, so appreciate the comment there. All right, so when we're doing this model, it's not quite just as simple as those temperature profiles that I showed before and evolving our chemical kinetic network, because things like the properties of the impactor actually matter as well. So things like impact angle, velocity, and radius all matter, where if you have a more oblique impactor, such as this one shown here, or if you have a lower velocity impactor or smaller radius, all of these effects will act to decrease the temperatures that are experienced during the impact. And at these lower temperatures, you're going to have increased survival of your molecules, including HCN. So we can take into account some of these effects, and that's what we do next. All right, so just to show you some of the abundance profiles as a function of time for various impactors. So at 5 degrees and 10 degrees, we can scale those temperature profiles for the corresponding impact angles, as has been shown can be done in the literature. And when we do that, we find that at 5 degrees, there's pretty much no degradation of either H2O or HCN. You have all of it that is initially there will survive at 5 degrees. Whereas once you go to 10 degrees, you have still most of your water survives. There's a little bit of degradation, as you can see in this zoom in plot over here in panel C, but the real change is what happens to HCN. So in the case of the full model that I showed you with all 77 reactions, that's this plus chemistry reaction, solid line here. So at 10 degrees, you have about 50% of your HCN will survive. Whereas in the model that we run for validation, where you don't consider the further chemistry, but just take into account HCN degradation reactions, you pretty much destroy all of your HCN. So this really shows how impact angle can change and influence the results drastically. So what we can do is we run these models for these 6 different radii shells for various impactors from 0 degrees all the way up through 90 degrees. And then we know what the impact angle probability distribution is from derivations and from calculations. And then you can use this to determine the impact angle averaged volume integrated HCN survival rate, which that's a lot of words. Basically what we're doing is we're integrating over the impact angle probability distribution and determining how the impact angle affects the HCN abundance to take care of that effect. Then also integrating over the volume of the comet over these 6 different radii shells. So in your outer shells where you have more material, these are going to have a larger weight in the overall survival of HCN. So when you do this, you find that about 2.3% of HCN will survive in your volume integrated impact angle averaged comet. So 2.3%, you would be asking, well, is that a lot? Is that not a lot? How does this compare? Is this significant? So that's what I'm going to talk about. So we also, there's one other caveat before I get into that, which is that these previous results were for a radius of 1 kilometer, velocity of 20 kilometer per second impactor as a fiducial impactor. Now, those effects of radii and velocity will matter. So what we can do is we can scale the results in the survival for different radii and different velocities. And then again, take into account the probability distribution of impactors over radius of velocity. And we do that, and then we determine what the global impact delivery of HCN will be. Another big unknown in all of this is how many comets actually hit the early Earth. This is something that's really highly unknown and unconstrained at the moment. So you can try to determine some constraints for this from geochemical evidence or theoretical calculations, but estimates range from anywhere from 0.1% of Earth's ocean water delivered by comets all the way up to greater than 10%. So we take 3 different cases, and for kind of the median case of 1% of Earth's ocean water delivered by comets, when you do this global impact delivery, taking into account the impact angle distribution, the radius distribution, the velocity distribution, and the total survival that we find there, you get 1.3 times 10 to the 14 kilograms of HCN delivered. So if you were to say that perhaps this happens over a period of increased bombardment, perhaps the late heavy bombardment, although that's becoming a little more contested as of recent days, I believe. But if this occurs over a period of, say, 100 million years, this would correspond to 1.3 times 10 to the 6 kilograms per year. So how does this source of HCN compare to other sources of HCN that have been evoked for the early Earth, such as atmospheric photochemistry or lightning generation? Both photochemistry in the atmosphere and lightning generation in the atmosphere are very dependent on the reducing state of the atmosphere, where if you have a more methane-rich atmosphere, these processes are going to be more efficient. So in those cases, you can get 10 to the 10 or 10 to the 9 kilograms per year in the reducing methane-rich atmospheres. If you go to CO or CO, so or what we find, or just to put value that we find 10 to the 14 kilograms, if we were to instantly dissolve this into the entire volume of water, it would be at a concentration around. And if you take into account this, and HCN is not, but instead under hydraulic.
All right, well, we seem to have lost Zoe for a moment there. Oh, no, now maybe she's back.
Looks like her mute is on.
Yeah, that's, I was just gonna say. Yep. Zoe, can you hear us?
Zoe, you're muted.
No?
Oh, now we hear you.
Okay, awesome.
Yeah, we lost you for most of this slide, so I'd recommend maybe starting from this slide again, and hopefully we won't lose you again.
Okay, so sorry. Thank you so much. All right, so basically, if another big unknown in all of this is how much of Earth's ocean water was actually delivered by comets. So estimates have ranged anywhere from 0.1% all the way up to 10%. So if we take these 3 cases, and especially here, I'm going to focus on the 1% region here. So for 1% of Earth's ocean water delivered by comets, we find that you have 1.3 times 10 to the 14 kilograms of HCN total will be delivered. Now, if you assume that there's 100 megayears of increased bombardment that this increased impactors are occurring over, this would correspond to 1.3 times 10 to the 6 kilograms per year. And if we compare this to other sources of HCN that have been invoked on the early Earth, such as atmospheric photochemistry or lightning generation, both of these processes are more efficient in methane-rich atmospheres. So there you can get 10 to the 10 or 10 to the 9 kilograms per year. So, but when you go to more oxidizing atmospheres, you get values that are closer to what we see for delivery. However, it's worth saying that if you take this total amount of HCN that we find for delivery and dissolve it instantaneously in the entire volume of Earth's oceans, your concentrations would be somewhere on the order of micromolar. Now, if you take into account that this occurs over hundreds of millions of years and HCN will hydrolyze in water on much shorter timescales than that, this is probably not likely to be an extremely relevant source of HCN on the global scale. So you might say, all right, well then, was all of this pointless? Does any of this actually matter? And I would say that perhaps it does matter if you don't consider the global scenario, but instead look at the local scenario. So here we'll picture if you have like a little piece of land and a comet comes in and impacts that land, makes a crater, and dissolves all of its delivered organics that survive impact in all of the water that it also brings. So in this case, you have much higher initial concentrations of HCN because you're not dissolving it initially into the entire volume of the ocean. Then what we can do is we can look at the hydrolysis rates of HCN into formamide and then into formic acid and ammonia, and determine how long HCN will exist in concentrations above the thresholds thought to be necessary for prebiotic chemistry. So this hydrolysis rate is going to depend on the pH and the temperature of the environment that you're in. And then the initial amount is going to be set by the impact angle and the velocity and radius of your impacts as well. So these triangles are showing you the total amount of HCN after 100 kiloyears after the impact in the local scenario. So you can see that under the more favorable conditions, say your lower pHs and your lower temperatures, you're going to have HCN lasting for longer than 100 kiloyears easily. Whereas if you go to neutral pHs and higher temperatures, by 100 kiloyears, it's pretty much all gone. So in terms of like an actual lifetime, so for 5 and 15 degree impactors at pH 6 and T equals 10 degrees Celsius, HCN will exist above millimolar levels for 200 to 300 kiloyears and above micromolar levels for 500 to 1,000 kiloyears. So this is then to tell you that if you can get your prebiotic chemistry to work with millimolar or micromolar levels of HCN in the time span of several hundred kiloyears, then this might be a relevant source of HCN for the early Earth and for your prebiotic chemistry. So in the future, I'm hoping to expand this to looking at survival of other molecules to figure out what the chemical composition of a comet pond might be, and then also look at other things such as HCN generation during impact from things like reaction of hydrocarbons, say methane, and nitrogen species like ammonia. So putting this back in the context of origins of life and this path, so I'm really hoping to be able to string together a way to look at the continuous path from the environment to the precursors of life and all the way up through protocell by considering not just the chemistry and not just the environment, but the interplay, and especially how the planetary processes and planetary environment supports this. So acknowledgements, I want to thank all of you for your attention and for bearing with me as I disappeared and reappeared. The UW Astrobiology community for having me and hosting me here. Professor Catling Barnes and Daniel Larson for organizing my visit, and I'm very excited to be coming here in the fall. And then also want to acknowledge my collaborators and co-authors on these two projects that I've talked about, the agencies I'm involved with, and also my pony Peter, who, this is him shown right here. He is going to hopefully be coming with me to Seattle, so if anyone is an equestrian or has advice on horse barns and things of that nature, I would be very thrilled to chat with you. Feel free to let me know. But other than that, just really thank you all again. I'm very excited for the future, and I would be happy to answer any questions that you might have.
All right, thank you very much, Zoe, for that fantastic presentation. On behalf of everybody, I'm going to applaud for you. That was great. Maybe you'll get some virtual applause, but I'm sure everybody is applauding in their bedroom or wherever they are watching. As I said at the beginning of this presentation today, that if you did have any questions, of course, many of you typed them in during the presentation, but if you have any more, please feel free and type them in right now, and I will pass them on to Zoe. It looks like we're already getting some of them coming in. So the first one is from Arshudi, who says, on a comet, how far can the Sutherland cyanosulfide photoredox network go, or does the pathway even occur? Also, I have read about comets containing amino acids. What pathways cause that production of amino acids on the comets?
So that's a great question. I would say in terms of the cyanosulfidic chemistry working on a comet, I would not be super optimistic about that, just because you need this UV light to drive it, and you probably need an aqueous medium for this. So there, I would say it might be much more plausible to take the initial contents of the comet that you want, such as the cyanide and the hydrogen sulfide or other sulfur-containing materials, get them to the Earth somehow, and then do your chemistry on a planet that can sustain and support liquid water. Now, if you have liquid water on a comet, say perhaps as your comet is coming through perihelion, and then you might have access to some of this light, perhaps you could get some of this chemistry going, and perhaps it could synthesize some of these amino acids. So maybe that's a way to get to some of these amino acids. As far as what the literature consensus is on how you synthesize amino acids that we find in comets and in meteorites, I'm not an expert in that, so I don't feel like I should comment too far on that.
All right, great, thanks. Before I go to the next talk, I do just want to point out to everybody who is on the line that it's nearly 4 o'clock here in Seattle, so if you did have another meeting, now might be the time to jump off, but I encourage you to stick around to hear some more of Zoe's answers to these questions. So I'm going to continue on here to the next question from Zach Cohen, who says, awesome talk, Zoe. Does water absorb significantly at the wavelengths you're using? And could the depths of the solution affect your results?
That is such a great question, Zach. So water does not absorb significantly at, say, 220 nanometers and above. Really where you start to get the edge of absorption for water is around 210, and especially like below 200 nanometers is where it really starts to absorb. So hopefully that doesn't cause too much of an effect. However, there is this big question of, when does water become self-shielding from the effects of UV light? And pure water, there have been some predictions for that, and it might be several meters. However, the issue is what happens when you put things in your water. So for example, do the presence of salts affect the UV attenuation or other UV absorbing material there? And so the group that I'm involved with at Harvard is engaging in this whole entire dirty water project, where basically we're putting stuff in water and measuring UV absorption to try to get a better idea of that. So that's something that's in progress, and hopefully can give you a better answer in a little bit on that.
Great, thank you. All right, the next question is from Joseph Foy, who says, great talk. Dumb history question from a supernova guy, but this comet business sounds a little like the old proposal of Fred Hoyle and Lou Frank about amino acids being delivered to early Earth by comets.
Yes, precisely. It's very much in the same vein as that, although I would say, like, the approach that we took in this project was to say, all right, well, amino acids might not be quite as abundant in a comet itself as something, simple that we can actually detect spectroscopically, like hydrogen cyanide. And since we know you can make amino acids from hydrogen cyanide, why not try to get delivery of the hydrogen cyanide from the comet and then do your chemistry on the Earth? So I would agree it's very much in the same vein as that, but the idea is perhaps cyanide is a little more abundant and perhaps it survives a little bit more. So that's our take on this alternative, but very much in line with that previous history.
Okay, great, thank you. The next question is from Kai, version 2, who says, do you have plans of studying comet ponds on asteroid surfaces? I'm trying to think if conditions on asteroids can be just right for the synthesis of RNA.
I think that's a great question. I'm not too well versed in asteroid containing water theory, but if you can get water on an asteroid body, which we know when you look at meteorites you do get signs of aqueous alteration, what probably did happen, then I would say studying chemical composition on an asteroid would be really interesting to see what sort of chemistry you can do on asteroids. And part of me really is intrigued by the idea of panspermia, I don't want to go so far as to say like I believe that that is the origins of life, but I'm intrigued by the idea, and I think the more we can broaden our horizons and expand how we look for origins of life, potentially to occurring off the Earth and on things like asteroids, I think that would be great and something wonderful to study.
Okay, great. Next question is from Stitzel, who says, perhaps radioactive material present within a comet or meteor would provide an energy source for the presence of aqueous water and subsequent molecular reactions?
Yeah, absolutely. So when you have the radioactive heating, especially like when you have aluminum-26 still existing in the early solar system, this provides a lot of heat and can generate these aqueous bodies on these things that are pretty far away from the sun and could be colder. So I think, yes, absolutely, that's something to consider.
All right, great, thanks. So there's not any more questions in the chat room right now, but I'm going to ask you one, and maybe more will pop in while I'm asking my question. So you discussed some of the issues that might affect the delivery of HCN to a planet, including things like radius and the angle of impact. But one thing you didn't talk about was the size of an atmosphere, the envelope. And I'm particularly thinking about planets orbiting low-mass stars that might need to have some sort of hydrogen envelope to protect them during the pre-main sequence phase. And of course, that's also interesting in terms of redox. So I was wondering if you thought at all about just, is there sort of a maximum envelope size, or how does that impact the delivery of HCN to the surface?
Yeah, that's such a wonderful question. That's a little bit beyond the scope of what we were considering in this first project. I would say it's something that we would hope to be able to include and be able to address in future work. So yeah, I would definitely love to hear thoughts on that, or be able to include that at some point. That's a little bit beyond what we did for this project here.
Yeah, sure. I just wondered if you had any thoughts on it at this point, but we can talk about it this fall. Yes. And while I was asking you those questions, some more have come in, so I've got some more for you. So next is from Roy Black, who says, is there a role for UV in making or degrading purines?
So purines are tricky. As of right now, there is not a great synthesis for getting the ribonucleotide purines. So people have been getting really close recently, and people are really pushing on this and trying to get it. So people can get the ribonucleotide purines just with like one or two wrong atoms, like an extra oxygen in the wrong place, or you can get the right nucleobase, the right purine nucleobase, but on arabino sugars, so the wrong stereochemistry, or you can get deoxy purine ribonucleotides in some cases. So getting very close, but as of right now, I would say there's not quite the synthesis of purine ribonucleotides. And the role of UV light in that is currently being investigated as well. So it's kind of consistent with the picture that we painted for the Sutherland chemistry, if it turns out to be possible.
Okay, great, thanks. And now it looks like probably maybe this is going to be the last question from Kabe, who says, great talk, Zoe. I have a clarification question. Is HCN synthesized by your impacts, or is it merely delivered? If delivered, does it survive the high temperatures produced by the impact?
So yes, that's a great question. We were considering delivery, not synthesis. So in the future, I'm looking to incorporate synthesis during impact. But here, this is just looking at the HCN that is contained in the comet that we can see today spectroscopically, how much of that survives impact. And you brought up the precise point there that as soon as you reach these threshold temperatures that are high enough to destroy the HCN, then no more of it will survive. So it's really at these lower impact angles where you don't have as high temperatures that you get most of your HCN surviving and being delivered.
All right, great. And one more has come in as well, so I got another one for you. This is from Arshuri again, who says, in the pyrimidine ribonucleotides pathway you described, is the irradiation cycle necessary for the pathway to occur, or a constant irradiation source, or can a constant irradiation source allow the pathway to occur?
So I would say most of the work has been done with like a constant irradiation source, at least in the laboratory. So that's what's been demonstrated before. And radiation cycles, I think they can provide potentially some useful expansion upon that, because if you need some reactions to occur in the light and some reactions to occur in the dark, a radiation cycle might allow you to do that. But I would say things like that are currently under investigation a little bit more. So we found that both irradiation cycles and continuous irradiation could work to turn C into U. Yeah.
All right, great. Well, thank you. Well, that is the end of the questions in the chat room. So I want to thank you again for that great talk and sticking around to answer all those questions. I hope to all of you that you all enjoyed it as well, and we'll see you next week at another AV seminar. And so to all of you, I wish you a good weekend to stay healthy and safe. And Zoe, we'll look forward to seeing you and Peter this fall. So take care, everyone. Hopefully see you next week.
All right. Thank you guys so much.